The second tool we'll talk about used for multivariate analysis of continuous data is multiple regression. Now previously we talked about simple or bivariate regression, but the multiple R is used to measure the effect of several predictor variables, independent and control variables, on one dependent variable. Now the assumptions of multiple regression are the same as those with the partial R and Pearson's R and simple bivariate regression. However, there are additional ones, things like multicollinearity that were mentioned previously. Also, all variables should be uncorrelated with the residuals of the joint multivariate distribution. So this is a check that residuals are a result of random error rather than some sort of systematic process. What we like about multiple regression is it allows us to disentangle the unique and individual contributions of individual predictor variables by pooling variable effects without duplicating joint effects. So what that means is we can control for and attempt to tease out those individual contributions of a variable, of a predictor, onto the dependent variable. And because we know about simple bivariate regression, the same logic applies to multiple regression. As such, it's easily interpretable because we are more familiar with the simple bivariate model, with little additional explanation needed to interpret the results. Now the disadvantages of multiple regression are the same as a partial R. As we input more predictor variables and control variables into the model, the things we have to examine become more complex, and so meeting assumptions is more stringent. Also, we need to be careful of multicollinearity and interactions between variables because joint effects are not additive but multiplicative. So it's very important that we tease out and isolate individual contributions when possible and look for interactions between variables as well. The formula for a multiple regression is very similar to the simple or bivariate regression. Notice the first part of the equation, that y is equal to a plus b times x. But notice the subscript of 1, which indicates the slope of the first variable times the value of the first variable. And then we have the second term, the slope of the second variable times the value of the second variable, plus the slope of the third variable times the value of the third variable, and on and on and on, plus e, which is just error. So we can calculate a predicted value for the dependent variable based on all the values we have for all of the independent and predictor variables. We'll have a constant generated by the model. We'll have slopes for each of the predictor variables. So this allows us to come up with a prediction for a particular case in the data by knowing the slopes and the values for the predictors. Now here's an example of what we would see in output from SPSS. This is very similar to the output that we saw for a simple bivariate regression. So the first box in the top suggests we're looking to explain the R square, right? The amount of variability of the model. So notice the subscript at the bottom, it lists all of the predictors in this model, and here there's only 2. So this is the same example as the partial correlation that we looked at previously. So we have general anxiety and fear. They account for 13.8% of the variability in the dependent variable. And if you look down to the box below that, you'll see that the dependent variable is safety precautions. The second box offers us the probability value for the model, which is the collection of all the predictor variables. And so when we look at the column labeled SIG, the probability value is less than 0.001. So this collection of predictor variables definitely has a relationship with the dependent variable, and they collectively explain 13.8% of the variability in safety precautions. Now that we know that the model in the aggregate is significant and explains 13.8% of the variability in the dependent variable, we can look to the coefficients individually to see how they work or how they contribute to that explanation. So this is the coefficients box. It looks very similar again to the simple bivariate regression that we ran in the previous lesson. So notice we have two variables listed here, the fear scale and general anxiety scale. And if we look to the right, we see the standardized coefficient for betas. They're both positive, indicating a positive relationship with the dependent variable. As fear increases, the number of safety precautions taken increases. As general anxiety increases, so does the number of safety precautions. This is what we saw in the partial correlation. And if we go further to the right in the table, we can see the zero order correlations and the partial correlations from the previous example. While we saw that the partial correlation for the fear scale was 0.194, remember it had been reduced from 0.365 to 0.194. Now we're also able to see the partial correlation for general anxiety and how it contributes to explaining general safety precautions taken. Additionally, in the middle here, we have a significance column where the probability values are listed. So note that the fear variable is significant with a probability value less than 0.001. But also notice that the general anxiety variable is also significant with a probability value of 0.020. This is less than our standard alpha level of 0.05, so it's also significant. So both these variables are significant in predicting the number of safety precautions. Typically, we would look for the standardized coefficients to determine which variable had a greater impact. So a one standard deviation change in fear, or in this case, a one standard deviation increase in fear, leads to a 0.28 standard deviation increase in safety precautions taken. Also, a one standard deviation in increase in general anxiety leads to a 0.106 standard deviation increase in safety precautions taken. So generally we would consider the fear variable the stronger predictor, or the better predictor in this case, because its standardized coefficient, or its beta value, is larger. Now if we look at the partial correlations, we see that 0.194 is a stronger relationship than 0.074. So the partial correlation tends to line up in order the way that the beta does, but this won't always be the case. In some instances it is not the same, or the order will be reversed among variables or in different order, and that's okay, just as long as we usually refer to the standardized coefficient or the beta value to determine the impact of the predictors on the dependent variable.